Hey everyone. So today we'll be looking at task scheduler. Let's see how many companies like to ask this question. Okay, a lot companies do like to ask this question, and let's see uh, what's this question about. Let's start a timer. Okay, given a characters array, given a characters array tasks. Okay, representing the task a CPU needs to do, where each letter represents a different task. Got it. Task could be done in any order. Each task is done in 1 unit of time. For each unit of time, the CPU could complete either one task or just be idle. Each task is done in 1 unit of time. For each unit of time, the CPU could complete either one task or just be idle. However, there is a non-negative integer n that represents the cooldown period between two same tasks, the same letter in the array. That is that there must be at least n units of time between any two same tasks. Return the least number of units of time that the CPU will take to finish all the given tasks. Got it. So basically, if A okay, given a character array tasks representing the task a CPU needs to do, where each letter represents a different task. Tasks could be done in any order. Each task is done in 1 unit of time. For each unit of time, the CPU could complete either one task or just be idle. However, there is a non-negative integer n that represents the cooldown period between two same tasks, the same letter in the array. That is that there must be at least n units of time between any two same tasks. Return the number of unit of time that the CPU will take to finish all given tasks. So my question to the interview would be, um, should I be expecting letters A to Z completely? Okay. And what is the cooldown period? What can be the cooldown period, I would ask? Um, and length of the CPU task, which is 10 raised to 4. Okay, got it. So that is that. My understanding of this question is like we have to find the least amount of units that are required to finish all the CPU tasks. So for every two same operations, there should be ideally a cooldown time of n in between performing both of them. So here, as in explanation A, we are performing B, then there is a idle time, then there is performing A, B, then idle time A and B. So total of 4 idle time is there, and for processing this 1 1 1 2 3 4, so that's why 8. There is at least 2 different units. Sorry, I just got a message. Oh, it's one of the Okay. Okay, no worries. So the time is ticking, but yeah, like A, B, idle. So let's see the second one. AA, okay, n is equal to 0. So this case, any permutation of size 6 would work. Yeah. Got it. Okay. So yeah, no more texting. So this in this one, A, B, C, A, D, A, F, G, A, idle. Why it has been idle for 2 seconds here? ADE, then AF, ADE, AFG, A, idle, idle, A. Like, is there a hint for this question? Because how will you use heap? Um, like how? How will you use heap in this case? Like, I understand that you have to take all the unique combinations, but in this case, okay, sorry guys, I'm getting a call. Okay, guys, so this is an interesting question. Using the example Using the example you gave, the problem with description is that it made seems like once you have executed say B, that you can immediately execute another A even if the cooldown period has not been met. Period must be met before executing A again. Using the example you gave, the problem with description is that it made it seems like you've So given here is breakdown, execute A. After this we need to okay, I guess we need to watch the
Hey everyone, welcome back, and let's write some more neat
Leetcode guy.
code today. So today let's solve the problem task scheduler. One of you suggested this problem, and I think it's a pretty good one. So we're given an array of tasks. It's a character array, and it's going to be limited to the characters from uppercase A to uppercase Z, so 26 characters. Each of the characters represents a task, and the task is something that the CPU needs to process. And the tasks could be processed in any order. Each task takes exactly 1 unit of time to process, so that's good because it makes things simple for us. And for each unit of time, the CPU could either process an entire task or it could be idle. And the reason it would be idle is because we're also given non-negative integer input n that represents the cooldown period between the two same tasks. And the same task is represented by the same letter, the same character in the array. And to understand this, let's take a look at an example. And by the way, what we actually want to return is the minimum number of units of time that the CPU will take to finish all of the tasks. Let's take a look at this example. We're given these tasks, right? 3 A tasks and 3 B tasks, and the idle time we're given is 2 units of time. So basically, let's say we processed an A task, right? That takes us 1 unit of time to process. Now we process a B task. And now we know that before we process another A task, we have to wait 2 units of time. So, let's say we process an A. We can't process another A. We have to wait 2 units of time before we can process another A. So what are we going to do in the meantime? Well, there's a B as well. So let's process one of the B's. And now for this B, we know we actually have to wait 2 units of time before we can process another B. So the next time we can process another B will be at this point in time after we have processed our second A. So now the question is, can we fill this spot with anything, or are we going to have to be idle at this point in time? And there aren't any other characters, right? We had 1 A and 1 B. Now we have 2 A's and 2 B's remaining, so we can't do anything. This has to be idle. We process an A, a second A, and a second B. That means that before we can process another A is going to be 2 units of time. So this B, and then another unit of time, and then another A. And we also processed a B. The next time we can process a B will be at this point in time. So at this point, again, we are going to have to be idle. But the good thing is that this is the entire, like all the tasks we were looking for, 3 A's and 3 B's. So as you can see, it took us 1, 2, 3, 4, 5, 6, 7, 8 units of time to do this, so our output is going to be 8. So now let's think about a general approach that we could come up with to solve this problem. So let's say we had this as our input. First thing to notice is we're going to be given characters A through Z. It doesn't really make sense to worry about which character we're looking at, right? There's really not a big difference between a B and a C, but we should keep track of how many of each character there is. So we know there's 3 A's, 2 B's, and 2 C's, right? We don't even have to worry about the characters anymore. We can just focus on the numbers. We know that there's 3 of one character, there's 2 of a different character, and then 2 of another character. We know that the idle time in this case is 1. What order should we process the characters in? It's probably better to process the more frequent character first, the more frequent task first, because we know there's going to be some idle time, and processing the more frequent one first basically gives us more time to not be idle. And I'll show you the intuition behind that. Let's say we did a C first, right? We do C, we know that the idle time is just 1, right? So then let's say we do B, and we're allowed to do another C right away. Let's say we do that, right? We do another C, and then we do another B because the idle time is only 1, right? So now we've already processed all the C's and the B's, and all we're left with is 3 A's. Okay, let's process one of the A's. Okay, great. But now we have an idle time. We have no other characters available for us, so we have to wait. And then we can process another A, and then we wait, and then process another A. So in this case, this was one way, but did this minimize the total time that it took us to process all the tasks? A different way would have been to start with the most frequent character, right, A, and now there's only 2 A's left. So now what's the most frequent? Well, you could say A again, but we know that there is an idle time of at least 1. So at this point in time, A is not available to us. So we have to process a different character, let's say a B. Then A is actually going to be available for us again. So we could process the A, or we could process the C. In this case, it doesn't really make any difference because there's 2 of each of these. So we could do either one. Let's just do C. So then there will be 2 A's, 1 B, and 1 C. Then we'll, of course, want to do the more frequent character, the A. And then there's going to be 1 A remaining. We can't process another A without at least 1 unit of idle time. So let's do B, and then do C, and then we can do A, right? This also is a valid way, and this one actually minimizes the idle time rather than this one. And what is the idle time in this case? It's about, not the idle time, the total time in this case is about 7 as opposed to 9 in the other case. So that's kind of the intuition why we're going to try to do the more frequent task first and then the less frequent task. How we're going to be doing this is by using a data structure called a max heap, which will allow us to continuously figure out which task is the most frequent one. And the max heap can actually allow us to determine that in log n time, right? If we have a bunch of these, we could figure out which is the most frequent in log n time, which is good. But in this case, actually, it's even better than that. It's about log 26, since we only have 26 different characters. This is kind of a constant time operation anyway. But I will say that the overall time complexity is still going to be big O of n. One, because we are going to have to, count the occurrences of each task. So we're going to have to go through the entire input. And we're going to be, popping every value from our max heap and adding every value to our max heap. So the time complexity is going to be big O of n. That's also going to be the memory complexity. But now to the actual algorithm itself. We're actually going to use one other data structure, a queue. It's not required, but I think it makes the problem a little bit more organized. So let's start off with the max heap, right? We have 3 integers. We're going to be adding integers to our max heap, not the characters. We're going to be taking the counts of each task and adding that to the max heap. So we're going to have a 3 and a 2 and another 2. And by the way, when I actually code this up in Python, we don't have a native max heap. So the way we only have a min heap, so the way I get around that is basically by taking each of these values and making it negative. In a max heap, we want to pop the maximum, and we can do that in log n time. So in this case, we'd pop the 3, which is the maximum. But in Python, we're actually going to do it the opposite way. All of these are going to be negative, so we're going to end up popping the minimum, which is going to be -3, but we're going to, assume that it's a positive 3. But yeah, so that's the idea. First, we're going to pop the 3 or the -3. You can think about it however you want. That's the most frequent, but now we want to change the count from being a 3 to now being a 2, right? Because we just processed one of the tasks. So, if you have a negative, you'll have to add 1. If you have a positive, you can decrement it to 1. In my case, when I write the code, I'm going to be adding 1 to this. But now we're actually going to be taking this and adding it to our queue data structure because we know that there's some amount of idle time for this task. At the current point in time, initially we were at time equals 0, but we just processed the task. So now we're at time equals 1. And we're going to add this integer 2 or -2 to our queue. But we're also going to be adding another value to the queue. And that's at what time is this task going to be available for us to process once again. Basically, at what point can we take this and add it back to our max heap, right? What's the idle time that is going to be remaining? Well, right now we're at time equals 1, and our idle time for each task is n equals 1. So basically, we're going to take n and add it to our current time. So it's going to be 2. Basically, at time equals 2, this task is going to be available for us to add to the heap again. So that's what the second value in this case means. And once again, we're going to pop from our max heap. We're going to pop the -2. And that means we have processed the task. So now our time is actually going to be time equals 2. We're going to take that task. It was a -2. We're going to add 1 to it, which is going to make it a -1. So then we're going to take that -1 and add it to our queue. And at what time is that task going to be available to add back to our max heap? Well, it's going to be 2 plus 1 because n is 1 in our case. So at time equals 3, this task can be added back to our max heap. But now that we're at time equals 2, we see that this task actually is available now to add back to our heap. So let's pop it from our queue and take the -2 and add it back to our max heap. And at this point, you're probably starting to get the idea, so I'll just kind of fast forward through this. We're going to pop this again, set our time now equal to 3. We're going to take that -2, add 1 to it, so it'll be a -1. We'll add that to our heap. At time equals 4, it's going to be available for us to add back to the heap. This value can be popped from our queue. We can add a -1 here and then start the cycle over. So let's pop this value over here, add it to our queue. We're running out of space, so let's add a little bit more space. That -2 will become a -1. The time now will actually be 4, so the time that this can be popped is going to be at time 5. We see it's time 4, so this can now be popped. So we add that back to our heap. -1, and now it's time equals 4. So I'm really going to fast forward through this. It'll take 1 more unit of time to process this task, but now this task, as you can see, we're going to pop it. It's a -1. We're going to add 1 to it, so now it's going to be 0, right? 0, once a task becomes 0, we know that we don't have to process it anymore, right? So when it's 0, we're not going to add it to our queue because it doesn't have to be idle. It's never going to be added back to the max heap. Once it's 0, we're not going to do anything with it. So, we pop it from our max heap and there's nothing left. But we see that this value over here, right now it's going to be time equals 5 actually. So time is 5. This can be added back to our max heap. Let's add that -1. Sorry if it's getting a little bit messy. But next, we're going to pop this from our max heap. It's going to become 0, so we don't add it to our queue. Now it's going to be time equals 6 after we process that task. And lastly, we have 1 task remaining. We pop it, we process it, it becomes 0. We don't add it to the queue. So now, after processing that task, our time is 7, so we can return 7 in this case. And that's pretty much the entire algorithm. So that's what I'm going to be following. Even though popping and pushing to a max heap is usually a log n operation, in this case, it's really going to be a log 26 operation. So the overall time complexity in this case is really just big O of n because we have to just go through every single task. Okay, now let's write the code. Okay, so now let's code it up. And you can see I have a couple comments just to kind of help simplify things for us. And I usually don't do this, but we want to count the occurrences of each character in the input. It's a list of strings. We could just, run through that, loop through that, and add it to a hash map. But you can actually do that with a built-in way in Python, just using a counter, which is literally a hash map. It'll just do that for us so we don't have to write the code. But now we actually want to create our max heap using those counts themselves. We can do that in Python with 1 line of code. We're just going to iterate through each count in the hash map that we just created, but we want to only iterate through the values, so count.values, and we want to add that to our hash map. But in Python's case, we can't have a max heap. This is actually a min heap after we heapify it. So I'm actually going to take the negative of the count and add it. So this is just creating an array with every negative count that we computed. But to actually turn it into a heap, we can do heapq.heapify in Python and to that max heap, and it'll basically order it. It'll take this array and order it in such a way that it is a max heap, basically for us to efficiently get the maximum value from the heap whenever we want it. We're also going to declare a variable to keep track of what time it is. Initially, we'll set that to 0, and we'll also have a queue, in this case, a double-ended queue. And the double-ended queue is going to actually contain a pair of values, and the pair of values are going to be that negative count that we had up above. And for that, task, that count, the corresponding idle time. At what time is it going to be available for us to add back to the max heap? Okay, so with that said, we're going to continue our loop. We're going to continue processing these tasks while the max heap is non-empty, or the queue is non-empty, right? As long as one of these is non-empty, that means we have more tasks that we need to process. So as we process, each iteration of the loop is just going to increment the time by exactly 1. And actually, before I even forget, I mentioned that the time complexity of this whole algorithm is going to be big O of n, but that's not entirely correct. Let's say n is the size of our tasks. We can add one more variable. Let's call it m, where m actually represents what the idle time is, because in the worst case, we have to go through that idle time for each task that we have, right? Suppose that the tasks was just an array of all A's. In that case, we'd have to go through the idle time for each task. But the idle time is actually a pretty small constant. I think it's less than 100 in our case, but just wanted to mention that in case. But okay, now let's continue with the algorithm. So at each iteration of the loop, we're going to increment the time by 1. If the max heap is non-empty, we are going to pop from it. And we can do that with heap q.heap pop from the max heap. And from it, we're going to get the count. And as we pop from the heap, that means we're processing this task. So to the count itself, we can actually add 1 to it, because remember, we're actually using negative values for the counts. If you were using positive values, you'd probably subtract 1 from it. But in our case, we're going to be adding 1 to it. And if this count is non-zero, we can check that like this. If count is non-zero, then we want to go ahead and append it to our queue, and we can do that like this. We're going to append a pair of values, the count itself and the time that it's going to be available again, and we can get that by taking our time, our current time, adding to it the idle time n. So at this time, we can once again add it to our max heap. Okay, that's great. We process a task, we remove it from the max heap, but remember, we also have to take care of our queue. If our queue is non-empty and the first value in our queue at index 0, the idle time for it, which is also which is actually going to be at index 1 because it's the second value in the pair. So if this time has just been reached, so if this is equal to the current time, that means we can actually pop this from our queue. So we're going to say queue.pop left, and so this is actually going to pop that pair of values, and from that pair of values we care about the first one, which is the count. So we're going to get index of heap. So we can do that with heap q.heap push. We're going to take it, add it to our max heap. So let's just copy and paste this and move it up above. We can just go a little bit. That's the entire code. So now let's just run it to make sure that it actually works. And as you can see on the left, yes, it does work, and it's pretty.
Okay, this is mind-blowing. This is absolutely nuts. Okay guys, I'll take a quick, okay, my camera just died, but I'll take a quick break and I'll be back in a minute. Hey guys, I'm back. So let's see what
Actually is a different solution for this. That's actually a little bit more of a true linear time solution, but I think it's a lot less intuitive. And I think this solution is perfectly fine for interviews. And because it's more of an intuitive solution, I think this is more or less what interviewers would expect you.
Okay, got it. So this task scheduler that we have, it's okay. So what we need to do is we need to create the priority queue, right? So that would be a max heap, a maximum heap, and basically before doing that we need to create a hash map, and for let I equals to al alpha alphabet of tasks. So if map dot has alpha, okay, let's do it in one line. Set alpha map dot get alpha or 1 plus 1 or 1. Okay, so this should do it, right? So let's see, console.log map. We should be able to see, yeah, A3 B3, so we are good here. Once we do that, do this, what we need to do is create a priority queue. Max heap is equal to new priority queue, and let's send in b minus a. Okay, so max heap so what we'll do is we'll loop through let val of map dot values max heap dot so I know push should be used, push val, and what should we use next in that matter, and let q is equal to an empty array. So while max heap dot size is there or q dot length is there, we have to keep doing this, and let time is equal to 0, return time. You have to return the time, right? So yeah, in that case, first of all, if max heap dot size is there, then will max heap dot, we need to pop the first element, right? why there is so I believe that we have to do dq, um, but will dq work as expected? Like, okay, dq, okay, so count at this point. What we need to do is reduce the count by 1, increase the time plus equals to 1, and also I guess we need to add that count q dot push the count and time plus n. Okay, so once we do that, yeah, and if q dot length is there and q dot o of 1 is equal to the current time, then we know that we need to add it back. Then q dot shift, remove that element, let old count and old time is equal to this, and we will basically add max heap dot push old count. Okay, so does that make sense? So tq, max heap or time plus 1, we are doing time plus 1 anyways. If max heap, then we are if count is, I guess if this time plus 1 is universal, and if count is there, then only we'll push this guy to the scheduler, like the queue, and when equal to time, okay, we have to pop the left and send the 0th element. And okay, if this doesn't work, then I guess then what is push exactly? Max heap dot okay, I guess we have to code it out. So class pq, let's call it pq, and let's do it for the last time. Constructor compare is there, or let's not exhaust ourselves with this. Straight away just copy paste this. Okay, let's be smart with our time. because we don't have the entire day to code this up and then make it work. Okay, so let's get rid of, let's call it pq dot add max heap dot pop, then add, so that should do it. Or will it, or okay, time limit exceeded, so max heap or q. Time plus 1 max heap dot size if it is there. Okay, max heap dot pop -1. If count is not equal to 0, okay, this is weird. Human readable. So max char, if char for if max char count equals to if char map is greater than max char count, so I'm doing the same effing thing. Why is this not working for me then? Okay, I did the same thing, man. So let's forget this. Just show me what is my heap looking like. Console.log max heap dot heap. Let's call it poll. Queue is empty, then time is 0. Console.log ma max heap dot size comma queue dot length. Why is it going out of bound? Like time, why time is exceeding? Okay, let's see. This is really killing me. Okay, guys, I guess that's it for this one. I'll see what's going wrong. I need to figure it out. Okay, I'll do it. Do the next stream, but I hope I'll be able to solve this one.